People trying to connect, we'll give them a minute or two, and then we will begin. Hello again, and welcome to our webinar about quantum internet enabled by space. My name is Charlotte Postma. I'm responsible for the space strategy at TNO, and I have the pleasure to introduce our session today. Before we start, let's go quickly through a few items of housekeeping. First, the webinar is recorded. Shortly after the event, you will receive a link to access the video. Second, we are quite numerous today, so the audience is on mute, but you have the opportunity to raise a question at every moment during the webinar via the chat, and after each section of the webinar, we'll be able to have a short Q&A. You will also have a few polls during this webinar. They are meant to exchange opinions as we go. There is no right or wrong answers, and the results are anonymized, so make sure you are comfortable to answer. There is no trick. And last but not least, we will have a short survey after the webinar to know what you liked and what we could do better for next time. With all this, I think we are all set to start our session of today. Many organizations across the globe acknowledge now that the overarching goal of quantum communication is actually the quantum internet. The networks that will enable to connect quantum devices all over the places. Yet, with the current status of technology, a global quantum internet cannot happen. The losses in fiber prevent quantum communication to happen over long distance. And that's where, increasingly, we see satellite contemplated as a possible solution. Yet, when does space turn out to be a better route than ground? What does a ground-space quantum network look like? And what kind of trade-offs need to be made between ground and space so quantum technology can really fulfill its potential? At TNO, we would like to help answering these questions, and we believe we have the right expertise to do so. Our people are knowledgeable about quantum technology, about satellite communication, and about classical networks, and this actually complements very elegantly all the work we are leading together with TU Delft on the ground, in QTech, and in Quantum Internet Alliance. But enough intro for now. Let me introduce our key speaker today, Dr. Gustavo Castro do Amaral, who is active in the field for more than 10 years. Gustavo, over to you.
Thank you very much for the introduction, Charlotte. I'd like to also extend a warm welcome to everybody that registered and is now joining us online. Before we dive right into the topic of the webinar, I'd like to propose a little thought experiment. Imagine that you have the most powerful computer in the world. It can render images at incredible speeds and crunch complex physical model simulations without breaking a sweat. Unfortunately, you cannot play video games over the internet with your friends or stream content online. Where's the fun? But more importantly, how can you push the limits of your machine and your own creativity in a bubble away from your community? That is why TNO is working towards enabling a quantum internet so that quantum computers can interconnect with each other and us with them. The more we study about the quantum internet, the clearer it becomes that such a network relying solely on a ground-based architecture is not going to do it. And that's because of the losses experienced in optical fibers. What has been, for quite some time, a futuristic concept, that of a quantum network in space, is no longer. Over the past years, we have witnessed a plethora of demonstrations of quantum communications experiments involving satellites. However, these are still extremely expensive, and the financial reward may be not clear. So in a word, they're risky. That is why we at TNO are working towards developing an architecture such that we can define when to best use a satellite and when to best use the fiber. So connecting nodes over free space, fiber, or even both. I myself have worked on the topic of quantum communications for over 10 years, but focusing only on the ground, because I had no experience with space. That is before I joined TNO and was exposed to the large heritage we have on testing, simulating, and building hardware for satellite communications. Building upon the models that we currently have at TNO for atmospheric optical transmission and the very operation of the satellites, we would like, again, to understand what is the benefit that we can extract from the satellites and how to do that. So with the framework that we're going to introduce today, we would like to demystify space and its role, make it a reality, and work towards achieving the quantum connectivity necessary to unleash the still unimaginable power of a network of quantum computers. So with that being said, I'd like to ask you, do you think quantum computers should be connected over long distances? Make sure to leave your question for us, or your answer for us.
So again, this is a small poll. There is no right or wrong answer, and results are anonymized. So feel totally comfortable to answer. And before we get all the audience voting, maybe Gustavo, I would be very curious to know what is your opinion on this question.
Well, I'd like to answer this question by saying back in the 80s, when the first classical internet links were established, we had no idea about how powerful they could become. And I think that also applies for the quantum internet. Maybe right now, connecting quantum computers may not be clear. Why is it so powerful? But I think it will be. So we should, indeed.
I recognize here your optimism. And we give a bit more time to the audience to get going in the vote. Again, don't be afraid, there is no right or wrong answer. I see now the result. We have 95% of the people online today who agree that quantum computers should be connected over a long distance and that are sharing actually your enthusiasm, Gustavo.
That is great. And that is also a great segue into the structure of this webinar. Again, as Charlotte mentioned before, we opted to break it down into 3 slots. And after each slot, we're going to take questions from you. And we're going to finish up the first slot by talking about the quantum repeater architecture. In the second slot, we're going to talk about the differences between space and ground quantum networks. And in the third slot, we're going to brush upon the challenges of the dynamics, or how the quantum networks evolve in time. Okay, so let's go ahead. When talking about the quantum internet, which can be a bit abstract for most of us, I'd like to start with something tangible. Imagine this map of Europe. And there we identified over 100 cities. And maybe in the future, these cities could be equipped with quantum computers. So if the quantum internet is available at that point, the goal of that quantum internet would be to interconnect these nodes. But how do we do this? Well, quantum computers use a certain resource to achieve the quantum advantage that is often talked about. And this resource is entanglement. So distributing entanglement to the nodes of our quantum network is what the quantum internet is all about. Obviously, multiple node configurations such as this one on the screen is quite complex. Maybe we can focus on 2 links, 2 nodes, and see if we can go about interconnecting them, let's say A and B. Well, a strategy to interconnect A and B by distributing entanglement to them is to first generate entanglement locally via a controlled process, and then use particles carrying the quantum information to take the entanglement to A and B. So we can introduce the first functional block of our quantum internet, the source. The source here is as general as possible. It's something that is able to generate entanglement and then distribute it to A and B. And because of the losses that we see between long distances, we want particles that experience low attenuation. And for that, the better candidates are photons operating in the band between visible and near infrared. So these have very long coherence times and low attenuation, which means that they can hold on to that quantum information as they propagate through our channels. So, okay, It doesn't matter really which platform our source is going to be based upon. What is clear is that it's going to have to have an interface with photons, a photonic interface. In order to simplify the sketch a little bit more, I will take the assumption that our source actually produces pairs of entangled photons. So we can go ahead and place our source right in between A and B. And remember, we are not focusing on a particular channel right now. So that channel could be either the fiber or the satellite. Okay, as I mentioned before, independently on which channel you choose, the losses are going to be a problem for you. So the loss is increasing, the distance is increasing. Is there anything that we can do better? Well, maybe if we could chop down this long distance in smaller stretches and try to, distribute an entanglement within those distances and then maybe put them together, that could be a more appealing strategy. So essentially concatenating things together. This actually is possible. And to talk about how this is possible, we have to introduce a quantum communication primitive called entanglement swapping or teleportation of entanglement. To talk about teleportation of entanglement, we have to talk about two things first. First, the BSM, our second functional block. The Bell state measurement is a measurement station that will receive our photons, and if the photons are there, it will produce a result that can be transmitted to the nodes A and B. But now the role of the sources changes slightly because instead of transmitting photons directly to A and B, the photons have different destinations. One of them is going to be kept at the nodes A and B, while the other travels to the BSM. Now, we have losses, so it's not entirely sure that these photons will live through the whole path. But if they do, both of them, and the Bell state measurement is successful in measuring them, again, it will send this information via classical channels to A and B. And this is where the magic happens. If that is done correctly, the photons that were kept at A and B are now left in a joint entangled state. So with that idea in mind, we can actually do what we set out to, which is break down the distances between A and B in smaller stretches. So we can have this smaller stretch on the left with two sources and a Bell state measurement. Another smaller stretch on the right with, again, two sources and a Bell state measurement. In between them, we will have yet another Bell state measurement, which allows the concatenation of these smaller stretches. Okay, that is great, but it's not really much of an improvement. Things change significantly when we introduce our third functional block, the quantum memory. The quantum memory, which we denote here M, is something that can hold on to the quantum states for a certain amount of time. And that completely changes things. Let's see how. Well, we go back to our case where we have the long distance between A and B broken down in smaller distances, let's say 2 in this case. And we interconnect them via the Bell state measurement. I'd like to take a moment here to say that these smaller stretches are so important that they have their own name. They're called elementary links. And if you concatenate these elementary links using the structure shown on the screen, you have a quantum repeater. Okay, let's see how it works. Again, our sources are going to be emitting photons, and they're going to be trying to reach the BSM. Because the BSM can tell us when it has been successful, when it does so, we know that the memories are now loaded with states that are entangled. That's great. Now, those memories are going to be holding on to those quantum states, and while they do so, the elementary link on the right can start attempting to generate entanglement and store them in their own memories. In fact, depending on how the quantum memories perform, they can try a number n of time. Okay, after some amount of attempts, hopefully the Bell state measurement will also herald or announce a successful result, which will leave the quantum memories of the elementary link on the right also in an entangled state. What is left to do is to retrieve the quantum states, send them to the intermediate Bell state measurement. And if that is successful, we're going to have entanglement between the states stored on the edges of our elementary links. And those edges are connected to A and B. Okay, great. That's how a quantum repeater works. But how much better does it perform? Well, let's go back to our initial architecture, right? The one without the quantum memories. It's useful to look at different time slots. I'm going to call them T1 and T2, just to represent two instants in time. Let's assume that at every instant of time, the elementary links are attempting to establish entanglement. So in time T1, let's say the elementary links on the left, both with memory and without, have been successful. Okay, that's great. Unfortunately, at the same instant of time T1, the elementary links on the right were not. Okay, we can try again in T2. In T2, however, the opposite happens. The elementary links on the left are not successful, but on the right, they are. Because the strategy without the quantum memories, well, cannot store the successes, they are not considered a simultaneous success and then not useful anymore. Because we have our memories on our quantum repeater, we can actually hold on to these individual or independent successes and then synchronize them together. Okay, that's how it works. But for physicists to determine whether they are better or not, we have to start assigning parameters, and the overall performance is going to depend on them. We can go ahead and assign efficiencies for the memory, eta m, and don't forget, we also have to assign a certain number of attempts that that memory allows you to perform. We also assign efficiencies for the source, for the Bell state measurement, and for the channels. Remember, the channels now are these smaller distances between sources and Bell state measurements, and we call it this small l. The efficiency of a channel is going to be a function of the losses, of the distance, sorry. So as the distance increases, the losses increases, the efficiency goes down. Okay, if we now take all these numbers, we can plot together the performance of different architectures. Remember, if you don't have a quantum memory, the number of attempts that you're allowed to perform is 1, and that's represented by the blue line here. We see that if the distance between the nodes A and B, for instance, increases, the chance that you're going to have entanglement between them decreases rapidly. However, if you have access to a quantum memory and it allows you to try a couple number of times, then your performance will increase dramatically. And the larger the number of modes, the better. Okay, a note here. Not all possible elementary links and quantum repeater configurations are the same. We choose to talk about memory, source, BSM, so that we can identify these more generic functional blocks. Different platforms will have different results. What's important to take away is that if we can, for each different configuration, assign efficiencies, number of attempts, and so forth, we can actually compare how different platforms, architectures will perform. Okay.
If I try to summarize a bit what you've taken us through, first takeaway, the quantum repeater allows transmission of entanglement over long distance. To do so, you want to distribute entanglement over shorter segments and then swap entanglement to the next segment.
Exactly.
And so this can happen. You need a quantum memory to store successful entanglement attempts until the next segment is ready for the swap.
Mm-hmm.
Let's see if we have some questions from the audience. I see we have a first question from Willem. What type of quantum system can function as a relatively long-lived quantum memory?
Well, first of all, thank you for the question, Willem. It's a great question. I think there are a number of platforms nowadays. I can think about crystals doped with a certain kind of ion. They're called rare earth ions. These are good platforms. There has been a demonstration of over 6 hours of storage in such platforms. There are also color centers in different crystals, such as the NV color center in carbon. There are also trapped ions. So actually the number of platforms is not insignificant. The thing about them is that sometimes they perform better in a certain function and worse on the other. So again, if you can assign these efficiencies and how they talk to each other, you can maybe figure out how to better position them and interconnect them to get the performance to the max.
And I see a second question. Brian is asking, what is making the quantum repeater so difficult to achieve?
Okay, so I guess a couple of things. The first one is obviously the fact that the harder you try to achieve entanglement, or let's say the larger number of photons that your source can generate, usually the quality of those photons or the entanglement reduces a little bit. So there is a balance between how much you can try and how high the quality will be. The other problem is the quantum memory. Usually quantum memories are really hard to do. And I'm going to try to paint a picture for you to understand. Imagine that you have the perfect quantum memory in the world, okay? You can store a quantum state there forever. What it means is that that system cannot interact with anything around it, and that's why it can store a quantum state indefinitely. But if it's that much isolated, then it also means that you cannot store anything inside or extract anything from it. So it's really a balance between being able to isolate it as much as possible from the environment, but still be able to interact with it so that you can store things there and then pick it up again.
I see many more questions. We will come back to everybody individually by email, but to keep the time, we may move to the second part of this presentation.
Okay, great. So again, we talked about the basic structure of the elementary link, and now we are ready to talk about the difference between space and ground quantum networks. Okay. Let's go back to our elementary link, and before we do so, I want to highlight the fact that these little yellow square that we see on the screen right now denotes things that are placed in the same location or the same lab. So as we saw before, the memory and the source are going to be placed in the same location because the source generates the photons, one of them goes to the long distance, and that's where we place our Bell state measurement, and the other photon is directly connected to the memory. The same thing happens on the other side of our elementary link, source and memory on the same location. Okay, with that being said, if you had access to a satellite, how would you go about positioning it in your elementary link? Well, maybe the natural solution would be to put it in between the two locations, because then the satellite is already at a long distance, which is more or less the function of the Bell state measurement. The problem here is that we start bouncing against some practical challenges of satellite communications. So what I propose is that we review some of them, the main ones, and try to resketch our elementary link to really make use of the satellite in the best way. So the first thing that is challenging about communicating with a satellite, it's the direction of communication. Remember, you're going to have a photon that is very precious to you, and you want to make sure that the losses on your photon are the smallest possible. In the configuration that we have on the screen right now, the Bell state measurement is in between. So if the satellite is carrying the Bell state measurement, the source would have to beam the photons up to the satellite. Okay. Beaming photons up to the satellite is a challenge. Why? Because imagine that your satellite is hovering at about 700 kilometers. For most of the path, your photons will not interact with anything. They're going to propagate through vacuum. However, for that first 10 kilometers of propagation, it will interact with atmosphere. And that interaction can lead to deviations of the initial path of your photons. And because after that initial deviation, you have a very long arm of 700 kilometers, you can really miss the satellite and then increase a lot your losses. On the other hand, if you have your photons coming from the satellite to Earth, again, most of the propagation is going to be through vacuum, but the interaction with the atmosphere is only at the last part, meaning that you're much less likely to miss the ground station. These two configurations are called uplink, when it goes from ground to satellite, and downlink, when it goes from satellite to ground. And as I just said, downlink is much, much more efficient, sometimes 100 times more efficient. One other challenge with satellite communications is the weather conditions. Not only does the cloud coverage completely attenuate your signal and make it impossible to communicate or to transmit photons, the fact that you have solar irradiance can completely saturate your detectors, and it has the same effect. Another problem is the availability of the satellite. If you have a satellite that is hovering, again, at 700 kilometers, it will have an orbit of about 1.5 hours, meaning that it will come by and it's going to be visible to you, and then it's going to go away, and only after an hour and a half it's going to come back. That is kind of a compromise because there are different orbits that we can place a satellite. One of them is the geostationary orbit. And there, the satellite is fixed with respect to the ground stations, so it's always available. Unfortunately, geostationary orbits are in excess of 30,000 kilometers, very different from 700 kilometers. And as I said before, the losses increase significantly with distance. So the compromise that we're left with is you either have continuous operation with extreme loss or intermittent operation with, well, lower loss. The final challenge about satellite communication, and in particular quantum communication, is the technical challenge related to placing some of our functional blocks on the satellite. In the case of the memory, for instance, it could be extremely challenging, although there are significant efforts being conducted at the moment. For simplification purposes, we could consider instead the source of entangled photons in the satellite, which have been demonstrated to work very well over the past 10 years. Okay, so with all that being said, let's start with placing the source on the satellite. This alleviates two issues. First, the technical challenge. We don't have to put the memory there. But also, it allows us to have a configuration where the photons are beamed down, downlink configuration, which is much more efficient. Okay, we have our ground stations. They're going to have memories anyway because we want to store those entangled states. The source is on the satellite. All is good. Well, not really. Because, see, the memories don't know which photons successfully propagated through the channel. The good thing about the other configuration was that we had this Bell state measurement that would let us know whenever a photon was successful. And that would allow the memory to say, oh, okay, this state I should hold on to. So sending the photon directly to the memory is not really a good strategy. We modify a little bit this structure to include sources and Bell state measurements in the ground stations. And now what happens is that the photons are transmitted by the satellite. They arrive at our ground station telescopes, are collected, sent to the Bell state measurement. There, photons from the source in the ground are also combined. And based on the simultaneous success of these two Bell state measurements, we know that our quantum memories are storing those precious entangled states. Okay, now one thing that is hopefully very clear about the elementary links independently on the configuration that we choose is the fact that they have to be able to concatenate together. And what's important here is that you have these memories on the edges of your elementary links so that you can then, with a Bell state measurement, interconnect and concatenate all your elementary links. What we see in this picture is that independently on whether it's fiber or satellite-based, we can indeed do that. Right. But before we start concatenating a hybrid network of things, let's evaluate them independently. And to do that, we want to take some simplifications. First of all, we are interested only on the effect of the distance on the performance of this channel. That means that we want the satellite to be static, so it's not moving anywhere, it's not in an orbit. It's really a physicist's simplification. Also, we want our operation to be during the night, so no stray lights and also no cloud coverage. So again, we're only interested in the distance and how the distance impacts the performance. One more thing that we need to do is start assigning numbers. To generalize a little bit, we say that memories and sources behave the same way independently on whether they're in the satellite elementary link or in the fiber-based elementary link. And that allows us to normalize this value. For those of you who are more into the topic, you understand that this simplification is outrageous. But for now, it allows us at least to look at how this impacts the performance based on the distance alone. The Bell state measurement is limited theoretically by an efficiency of 50%, so that's the number that we assign. And as far as the number of attempts goes, 10 is actually a reasonable number. So we move on with these. So for the ground station, the distance between them, if we're going over ground, is, well, just this distance L, as we talked about before. Unfortunately, the losses in the fiber scale exponentially with distance. So that means that very dramatically and very quickly as the distance increases, your losses are going to prevent the communication. On the satellite, however, and again, let's imagine that our satellite is hovering at about 700 kilometers altitude above ground. The distances to interconnect these two ground stations via the satellite are a bit larger. Let's say L prime, just to differentiate from the initial L. Although larger, L prime is a bit easier because the losses in free space scale quadratically. So the losses of the photons coming from the satellites and propagating over vacuum will essentially scale in a smoother way as opposed to those in the fiber. A couple more things need to be considered so that we can make this comparison of the performance more interesting. The first thing is, how well can a satellite equipped with a source aim at a ground station? Well, we're limited by some things here, but we can achieve beam diameters of our beams generated by the satellite of about 10 meters at the ground stations, and that is at a distance of 700 kilometers. That's quite an achievement. However, telescopes on the ground stations cannot be much larger than 2 meters because of technical challenges. So we're going to have a lot of loss because of that. Another problem is the accuracy of the satellite aiming at the ground station. Again, with current available technology, we can find an error of about 1 meter. Great. So now we have everything that we need to start comparing these things. So let's go back to the different architectures that we can have. The first architecture is simply a elementary link, and we change the distance between the two nodes that are being connected. Again, because of the exponential losses of the fiber, this performance severely goes down as in the first 100 of kilometers. We can optimize this link by dividing it in stretches, effectively a quantum repeater, and concatenating the elementary links, right? So you see that the performance is significantly increased. When we introduce the satellite, something interesting happens. At the beginning, at the shorter distances, the satellite performs worse, and that's expected. But as the distances approach hundreds of kilometers or even thousands, the satellite is significantly more beneficial than the fiber connection. Okay, that's a very interesting conclusion. So how does this map back to our European quantum network? Well, we have here 100 cities, remember, with nodes equipped with quantum computers, and we want to connect all of them. But connecting all of them is quite complex. So let's use a mathematical tool called a graph. A graph is simply the expression, the mathematical expression of how hard it is to interconnect a certain set of nodes. Let's say these 4 nodes here. These edges touching each of the nodes are called edges, and each of them have weights. The weights here, again, translate how hard it is to connect the 2 nodes connected by those edges. And naturally for us, those weights are going to be proportional to the probability of distributing entanglement between the nodes. If we assume that the yellow connections are fiber connections, that's all well and good. But we can also introduce connections, the orange ones, based on satellites. Now, if we have this structure and we write down the weights of the edges of our graph very well, using the performance that we established before, we can run efficient algorithms that try to estimate the best path, or in other words, given a certain combination of nodes, what is the best route to go from one to the other? Let's assume that because the nodes are separated by a long distance, it's more beneficial for the algorithms to find a solution through satellite. Well, that changes if, for instance, one of the nodes is covered by clouds. That will increase the losses significantly. And then if we run the algorithm once again, it will prefer to go through a different path. For instance, one that combines satellites and fibers, or maybe one that is only via fiber. Okay, so we want to take this graph best path approach and apply it to our European quantum network. Taking all the combinations of all the possible 100 nodes would be super complex and take a long time. So what we do is that we sort randomly pairs of nodes and try to find the best path. On top of that, for each of the nodes that are sorted, we also look at the history of weather conditions in those locations and include them into the analysis. And we do that also randomly. For each pair of node and each possible weather configuration, we sort 10,000 cases. And for each case, we plotted in a graph the result. We color-coded for you. So in blue here, we see the results where the best path in our graph was chosen to be all fiber, as expected, because we have distances below 500 kilometers. When the graph starts picking those distances that are above this threshold, however, we see in black solutions that are considering only a satellite. And the same trend that we saw in the previous picture is again reproduced here. So even in the presence of weather conditions, the satellites can be beneficial. Also interesting is the fact that our graph sometimes provides solutions that combine both satellite and fiber and are here represented in red. So this analysis, again, allows us to determine whether you go via fiber, via satellite, or via both. And being able to know which one is great to, in advance, determine what's the best performance achieved by your quantum internet. Okay, so I talked a lot about how it's hard to do it, but I'd like to ask you, with all these challenges, how long do you think it's going to take until we have access to the quantum internet? Maybe less than 10 years, 10 to 20 years, or more than 20 years?
This is the second poll of this webinar. Again, there is no right or wrong answer. Make sure you are totally comfortable to participate. And before we get the opinion on the audience, I would be very curious to know what you think about that, Gustavo.
Okay, so I'm known for being a very positive person. So I think that maybe not necessarily a global quantum internet, but I think that in the next 10 years, we're going to start seeing the impact of the quantum internet in our lives. So I'd say less than 10 years.
Less than 10 years? I see people are still voting. We'll give them a few more seconds before we announce the results. I'm still waiting for the final numbers here.
I hope it's not all above 20 years.
Now, I see the majority of the audience today is convinced that it's between 10 and 20 years. We have 67% there. Small number, in fact, are with you. Well, still 25% of the audience. Okay. And we have the rest that is a bit more doubtful about the immediate fullness of the arrival of the quantum internet. Again, if we try to put this webinar in a box, what should we keep from this second section? First, satellites have operational constraints. They are not an easy technology. First, you have to go through the atmosphere, which is challenging. Second, you have the weather, which has an influence and which can block operation in case of cloud. The question of availability is central and is determined by the configuration of the constellation. And it also implies, and this is not trivial, to put some quantum technology in space. Yet, even considering all those things, those challenges, they have turned out to be strongly beneficial for long-distance quantum communication. And this best path approach that you led with the team around the European context has shown it, even taking into account the weather forecast. Let's see if we have some question now from the audience. I see a first question here from Simon. Mm-hmm. Simon is asking, would you say that quantum memory is absolutely necessary for establishing quantum internet?
Okay, that's a good question. Simon, that's quite a technical question, actually. In fact, there are several papers in the literature that don't use quantum memories. These are called all-optical quantum interconnects, and they use something called cluster states. So the demonstrations of these all-optical quantum interconnects is, as far as I know, not present yet. They are quite challenging to achieve, but no, it's not necessary to have quantum memories to achieve a quantum repeater, but is the avenue that most of the research groups and organizations studying this problem are taking right now.
And I have a second question here from Antarik Shah. He asks what could be an ideal candidate for the entangled photon pair source?
Okay, that's a very good question. So thank you, Anta, for asking that question. I think that there are certainly a lot of interest in these sources based on spontaneous parametric downconversion. Is a nonlinear process in a crystal. It's very simple because all you have to do is take a crystal, pump some laser into it, and you have your photons coming out. The problem is that the generation of the photons is not deterministic. You pump and sometimes it happens, sometimes it doesn't. And what a technology that is now gaining a lot of traction is that of quantum dots. And in quantum dots, you drive your system and almost deterministically you have your photons being emitted. I think for the future, probably for the short term, these sources based on crystals and lasers are still going to be the choice. But as we approach better level of control of these quantum dots, probably they're going to take over.
And I see we have really a lot of questions. Because of time, we will not be able to take more, but everybody will get an answer via email. Thank you for your interest. It's really appreciated. I think we can move now for the third part of this webinar.
Okay, so now we're talking about the dynamic quantum networks. So that means that we're going to analyze how the condition of our channel or the performance changes over time. So we go back to our original sketch where we have satellite. It has a source in it, and it's beaming photons down to Earth that are going to be collected by our telescope and sent to our Bell state measurement. Imagine first that we're operating over the night. The sources of noise or stray photons during the night are quite limited. These are light pollution in cities or the reflection of the light from the sun in the moon or stars. So if we look at the photon, the precious photon coming from the satellite to the ground, we see that along with it come a couple of other photons, again, the noise. These photons are collected by the telescope and sent to the Bell state measurement. The Bell state measurement will perform a measurement, but the quality of this measurement will degrade if there is more noise. And we can actually quantify how much it degrades by looking at the fidelity. The fidelity is a concept that allows us to determine how close together two quantum states are. So imagine that the sources, both on the satellite and on the ground, are generating perfect quantum states. Then without noise, the Bell state measurement will be able to perfectly give you a result. But if you have more noise, the quality of the result of the Bell state measurement will degrade. The fidelity will degrade. This is even more drastic when we're operating during the day because the solar irradiance, the amount of photons that are coming into your telescope is really large. So unless you have a good strategy to filter these photons out, the fidelity of your Bell state measurement is going to be not high enough for you to have your quantum communications. So there are three different strategies to be able to filter out these photons. That is a spatial filter, a temporal filter, and a frequency filter. So the idea is that we stack these filters together to try and remove as much as possible those noisy photons and keep only the one that we are interested in. Well, unfortunately, the strategy of filtering that gives us the best results is also the more technical challenging. So the one that gives us the best results is the spatial filter. How do you filter spatially? You can imagine that the photon coming from the satellite has a very particular direction, and the photons coming from the sun, for instance, come at every possible direction. So if we can restrict the direction at which the photons are coming from, we can really remove the photons coming from the sun. However, in order to increase how restrictive we are in our space filter, we also have to become more and more accurate in how we aim our photons from the satellite to the ground station. So the way to quantify how spatially restrictive our telescope can be is by using a figure of merit called its field of view. So if the field of view decreases, we're more spatially restrictive. If it increases, we are allowing more photons from other directions to come in. If we evaluate how the noise and therefore the field of view impacts the fidelity, we see that with data from solar irradiance measured over a few hours in the ground, we can achieve high fidelities of the Bell state measurement when it's during the night. But when it's during the day, depending on the field of view that we can achieve, we really lose the quality of our measurements, going down to maybe 30%. Unfortunately, right now, with the accuracy that we can achieve in our satellites, we are limited by the green curve that you see on the graph. So currently, we cannot really do quantum communications from a satellite during the day, but we can definitely improve on that to achieve that blue line that we all want. One more thing that is interesting to analyze here dynamically is the very orbit of the satellite. As I mentioned before, the satellite that is hovering at about 700 kilometers will come and go at a period of about 1.5 hours. That means that during a certain amount of time, about 10 minutes, it will be visible to the two ground stations, interconnect them, and then go away. And then it's going to come back. It's going to interconnect the ground stations again for a limited amount of time, go back again, and so forth. So if we look over time at how much entanglement you're generating using that satellite, that's the result. At limited windows of time, you have that entanglement being generated. So that's not very good. But what we can talk about here is a constellation of satellites rather. And that constellation of satellites needs to be synchronized in a way that if a satellite is going away from the visibility of the two ground stations, another satellite can come and take its place, and so forth. So if we can achieve this, we can actually make sure that the constellation of satellites enables this availability or continuous availability that we want. Obviously, that's not an easy task, and it can also increase the amount of effort that you need to put into your system. You have to have more than one satellite. We have calculated about 10 to 20 satellites to make it a reality. Okay, so now we want to take all these dynamic impacts of the performance of our quantum channel, and we want to analyze them in our best path strategy. The problem now is that because we have a lot of dynamics going on, we cannot analyze all the nodes all the time. So we pick 3 nodes that are quite representative of the message that we want to have you get from this webinar. The first link is the Vienna to Zagreb link. It's a shorter link on the range of 260 kilometers. So if we go and try to run a best path between these 2 nodes, we find that the entanglement generation that we can achieve using a fiber is all the time much higher than that we can achieve using a satellite. And that's kind of expected because it's a shorter link, so the losses in the fiber are still much smaller than the losses achieved using a satellite. And that's not even considering the effects of the stray light, so the light coming from the sun, the noise, or the one from the weather. Again, the weather changes over time, and then the losses in the channel will also be dynamically changing. What we can see from here is that on the second graph in the middle, if we are operating during the day again, our fidelity is super low and probably the quality of our quantum channel is not going to be very good. On the second link, the Lisbon to Madrid link, that's a bit longer. It's about 500 kilometers. And now the effect on the distance is clear because whenever the satellite is available, it performs better than the fiber. However, will that still be the case if we consider the weather and the noise? Well, before we go into the results, let's just introduce the third and final link, a link between Berlin and Budapest. There, we see what we expect. Now, because of the losses of 700 kilometers, the satellite is orders of magnitude better than the fiber. Again, let's see if that still holds when we include the dynamics of noise and weather. Unfortunately, results for Vienna Zagreb are not very interesting because, as we talked about before, the fiber is performing better than the satellite. And really, the dynamics in the fiber are not that significant. However, in our second link, the Lisbon to Madrid link, we see very clearly that during the night, the best path is to go via the satellite. And in this case, we are considering a constellation of satellites. But during the day, the system chooses to go through the fiber. The same is true for the third and final link, the Berlin to Budapest link. Here, we see that the performance of the satellite on average is much higher than that of the fiber, but it's still, because of the limited fidelity of the Bell state measurement, we choose to go to the fiber sometimes. I think what's the conclusion of this slide is that there is no clear winner. The best path to go is to have the flexibility to choose what is the best option at a given time for a given node. And with that, I'd like to send that question to you on the audience. What is the most attractive network configuration in your opinion? Fiber, satellite, or both?
That's the last poll of this webinar. Again, no risk in answering, just give your opinion transparently. And before we can see what the audience is feeling, let's see, even if I have a strong guess of what will be the answer, what's your opinion, Gustavo, on that question?
I think this question is very much related to the first one. We asked if you think that the quantum computers should be connected over long distances. And in long distances, we really mean a distance that covers a continent like Europe or even the globe. And if your answer is yes to that, and my answer is yes, the results show that, yeah, the fiber alone will not cut it. But it's not that it's not useful. It's extremely useful for metropolitan distances. So the combination of both is really what we should be working on.
Excellent. And I must say we have an absolute winner on this question because 100% of the audience has voted also for hybrid. So I guess you made a good job in demonstrating this. The third, let's fill in the third and last box to take away from this webinar. Getting rid of the noise is still a significant challenge. So we can use satellites in the future. So that will require probably more work. The hybrid quantum network is the one giving the best result over long distance. And to do so, you probably want a switch, ground and space, to be able in real time to optimize the best route. Yes. With all this, let's see if we have another question from the audience. I see a first question from Eda. Eda is asking, is quantum internet only for connecting quantum computers or also a way for normal computers to connect super safe?
Great question. And I would say yes. Edar is already providing the correct answer to his question. Yes, it can also be used for computers to communicate in a secure way using quantum key distribution or other quantum cryptography protocols. The idea is that if you have a quantum internet and you can distribute that entanglement between any set of its nodes, as we talked about in the beginning, QKD or any other quantum cryptography protocol is a way to extract from that entanglement bits, classical bits, that are protected by the laws of quantum mechanics and then can be used in classical communication. So it's not only for quantum computers. I would say that that overarching goal of connecting quantum computers could achieve certain unimaginable things like simulating the universe or molecules. But indeed, the security of our classical cryptography can be extremely enhanced by our quantum internet.
I have a second question here from Alessandro. Alessandro is asking, what kind of satellite would, in your opinion, better respond to this need? And I think he's referring to CubeSat, SmallSat. What type of satellite would be a better match for this?
Great question. Okay. So I would like to use the fact that we highlighted the existence of a constellation to answer this question. My personal opinion is that unless you have the requirements to increase the complexity of your infrastructure inside the satellite, and by that I mean maybe you want to put a quantum memory there, unless you need that or unless that is a requirement, it's better or maybe more efficient, cost-effective to have as small satellites as possible, like a CubeSat, and place sources there. Sources can be made quite small and quite efficient. So having many satellites with many sources, at least right now, could be much more efficient than having more complex satellites. It's still going to take us some time to have that infrastructure. So I think right now, or for the next 10 years maybe, let's have several satellites, small ones, with sources in the sky.
And I see another question from Laurent. Laurent is asking, are you developing space-compatible quantum memories and entangled photon source?
Yes, thank you for the question. It's a pleasure for me to be able to say that, yes, we at TNO are developing both. So quantum memories that could potentially be compatible with satellites and also sources of entangled photon pairs. Yes, we are doing that.
And as a person responsible for strategy, I would like to join Gustavo saying we are also looking for partners to write this part of the story. So if you're interested, please knock on the door. I think we have a lot of questions. I'm really sorry we cannot go through all of them. But again, we will come back to each of you individually. And we are very grateful because it shows a great interest for the thematic. We are going to conclude our webinar here. So we will reach out quickly to you for the recording and for the little survey. I hope you enjoyed the session as much as we did, and that you take away a little part of our big enthusiasm in sketching what will be the role of space in a quantum internet. On behalf of TNO, thank you very much for listening and have a very good day.